we are finally here. It is time to start hypothesis testing. Let's go. We're going to review briefly why this matters again. Why are we doing this? We're going to talk about how unlikely or likely something is, and we can use our Z and T cutoffs to determine that. We're going to talk about the logic of hypothesis testing and our little problem of confirmation bias. We're going to talk about the null and alternative hypothesis, one and two-tailed tests, and we're going to practice formulating some hypotheses. So why are we doing this again? Why does this matter? The core of this is that things are uncertain and we have to try to quantify them with probabilities. It's not uncommon to observe one student with poor academic performance or one building with high levels of lead in its water. This may not be groundbreaking news or require any attention, but what if we saw an entire city or a state of students with poor academic performance or high lead content in the water? This is much more unlikely and may be worth further investigation. But now we have to figure out how unlikely does something have to be for us to conclude that there is something going on that we need to go and investigate. A fairly common convention in statistics is to test how likely something is. For example, assuming that the water is fine in Flint, Michigan, and the probability of seeing this high of lead content in the water is less than 5%, do you think that there is something wrong with the water, or do you think it's just a fluke? What if instead the probability was less than 1%? Do you think there's something going on? If the probability of seeing this high of lead content in water is less than 5%, we would say the results were statistically significant at the 0.05 level. That 0.05 level corresponds to less than a 5% chance, and this is related to our 95% confidence too. There's also this 10% chance, but it's not used very often, and there's this 1% chance. And though this 0.05 is most common, it depends on the context. In high-stakes situation, like a pharmaceutical drug, this 0.01 might be the cutoff used. When we're testing something, we want to have some confidence, or said another way is we want to have a certain level of significance. Now that's great. We can say this 5% or this 1% kind of cutoff, which is fabulous, but how do we know what the standardized value is that corresponds to that 5%? Well, if we were using the Z table and sigma is known, we already know the values. These do not change if sigma is known. We've already been dealing quite a bit with 1.96 and a little bit with this 2.58. Sorry, 90% confidence, nobody really acknowledges you. But many times we don't know that sigma, and sample sizes can be kind of small sometimes, so we usually need to use the t-distribution. All these confidence intervals, levels of confidence, levels of significance, cutoffs, they're going to finally help us move on to hypothesis testing. So we want to know if there are patterns and differences between groups, say a control group and an experimental group on some sort of a drug. And if so, are those differences true differences or just due to random chance? We know how finicky samples can be, but using distributions and confidence intervals, we have a much better chance of getting closer to the truth. If we assume everything is fine and everything is the same, what is the likelihood of getting this outcome by just random chance? We've been doing this with our Z and T tables to determine the probability of observing a certain value. Now we are going to start finally using all those skills to run a formal hypothesis test. Hypothesis testing, it's time. Let's do this. So going beyond the mean. So far we've been calculating these confidence intervals for a statistic of interest like the mean. We have some value in the middle and we add a little bit on top and a little bit on bottom to make sure that we capture the truth. But rarely do we want to just know the mean of one group. What are some more interesting research questions? Think of a few that are of interest to you and let me know, maybe in a comment or somewhere. Tell me, I want to know. So here are a few that I came up with quickly. Do females have more empathy than males? Are men better at spatial tasks than women? Does exercise plus diet work better than just exercise or diet alone? Do more confident people make more eye contact than less confident people? Are certain racial and ethnic groups more likely to get accepted to a particular university? Are certain racial and ethnic groups more likely to experience police violence? Does this drug work better than this placebo? These are all wonderful, curious questions. So some of those examples I just showed you may seem fairly easy to answer, but we now know just from the way samples work, all samples are going to vary a little bit from one to another, and how much actually counts as more. So for example, do females have more empathy than males? Maybe some females have more empathy, but what about those more empathic males? How much more empathy does one group have to have over the other for us to say there is a difference? Would a half a point be considered a real difference? Or do you need 10 points? How much is enough? we have to find a way to quantify. Before we start quantifying, we have some assumptions that we need to address. To conduct hypothesis testing, certain assumptions need to be met in order to run certain statistics. One of them that's very important is the data was collected using randomized sampling. Some other assumptions sometimes include a certain sample size or a certain shape of the distribution that it has to be normally distributed. Not all data is. And assumptions differ depending on what population parameter you're trying to estimate and depending on your research question. Assuming that all your assumptions have been met, you see what I did there? Then you can start the step-by-steps of hypothesis testing. As a quick side note, I've seen in other books and online that some people will break this up into more or less steps, but the idea is the same. Step 1, state the hypotheses. There will always be two hypotheses. They come in pairs. So we have the null and the alternative. Let's look at the null first. Here we have h sub 0 is one way to write it. And usually this is just like the norm or the status quo. It's the assumption that there is no difference and everything is cool, there's no effect, there's no change. So as a researcher, many times this is the thing that you want to reject. For example, there is no difference between the lead content in Flint, Michigan water and the water in the rest of the US. Conversely, the alternative hypothesis, denoted as H sub 1 or H sub A for alternative, this is usually the idea that you are trying to provide evidence for, the new idea, the difference, the novel thing. As a researcher, it's usually your big idea and that thing that you kind of believe and you're trying to test. For example, there is a difference between the lead content in Flint, Michigan's water and the water for the rest of the US. So usually your null and alternative are the same thing, usually just different by one main word like no, not, something like that. Let's have an etymological moment and look at the word null. So to nullify something means to invalidate or to cancel it out. When something is null, it means 0. In hypothesis testing, we usually want to nullify the null hypothesis. We want to get rid of it, cancel it out. We typically want to reject the premise that the difference is 0. Here is the evolution of the word null. Good stuff. So the general assumption of the null hypothesis is that there's nothing there. There's no difference, there's no effect, there's no relationship between these two things, there's no difference between the groups, and everything is cool. The alternative hypothesis is usually the novel assertion that there is something there. There is a non-zero difference. There's an effect. There's a relationship between these two things. There's a difference between these two groups. And in some cases, everything is not cool. So let's take a quick detour into the logic of falsification. In statistics, we never really prove anything, we only provide evidence for some things, like the alternative hypothesis, or evidence against other things like the null hypothesis. This is how science works, by disproving other explanations for a phenomenon. To support and hold your belief, you need to be able to reject the opposing argument. We assume the null is true and test how likely a certain outcome is based on that assumption. This is incredibly important, and I will keep repeating it again and again. Now let's briefly address confirmation bias. I love this cartoonist, chainsaw suit, look him up. So I'm sure this has happened to you before, that I've heard the rhetoric from both sides. It's time for me to do my own research to find the real truth. Literally the first link that agrees with what you believe. Jackpot. We all fall victim to this. Unfortunately, we tend to look for and accept things that agree with and confirm our beliefs while disregarding others that don't. And now, with the way that social media works, a lot of the content that we consume is filtered specifically to be in line with our interests and beliefs. This is not always the best thing. Makes for some interesting scrolling. Here's an example that goes back, I believe, centuries, and it has to do with all swans are white. It has a few different meanings in a few different contexts, but for right now, I'm going to be discussing all swans are white in the confirmation bias realm. So let me prove to you that all swans are white. See? There's a white swan, there's a white swan, there's a white swan, there's so many white swans. Obviously, all swans are white. But what is this researcher missing? What should they be looking for? Not more white swans. They should be looking for the one black swan, and I don't mean the movie. It only takes one black swan to disprove that theory that all swans are white. Rather than looking for more white swans to amass your white swan theory and collection, you should be looking for that black swan. Ha 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 ha, I stomp on your theory. You should have paid attention to your own biases. Quack. Let's quickly talk about the nitpickiness of the hypothesis language. We only ever reject or fail to reject null hypotheses. We never accept any hypotheses, only retain. And at the end of any hypothesis test, you will make one of two possible conclusions. You will either say that you fail to reject the null hypothesis or you reject the null hypothesis. We never make statements about the alternative hypothesis in regards to rejecting or failing to reject. Remember, in hypothesis testing, we always start from the assumption and that belief that the null hypothesis is true, that we live in the null world. Usually this means holding the opposite of your actual research belief in your alternative hypothesis. But you will always assume we live in this null world until we can test it and reject it. Now that we have the language down, let's talk about the notation. Whenever we do a hypothesis test, we are always making assertions about the population at large. So the parameter that we're interested in is mu. You want to go beyond that sample, that x bar, and say something about the population. So you will always use mu because of this. Never ever x bar in your hypothesis notation. Hypotheses always come in pairs, as we now know. And one of those two pairs always has an equality symbol in it. The equality symbol either equals or is less than or equal to or greater than or equal to, that is always linked to the null hypothesis. The alternative always has just the inequality part, so not equal to, less than, or greater than. So here are three different types of hypothesis testing situations. We have a two-tailed, one-tailed left, and one-tailed right. We're going to go into more detail on these in the next slide. But for now, notice how the notation, in all of them we are using mu, and the top one, the null hypothesis, is the one that has an equality symbol in it. So this one is less than or equal to, greater than or equal to, or equal to. And our alternatives are either not equal, less than, or greater than. And now let's look at some examples of these. Here are those three different hypothesis testing scenarios. In this one, we're doing a two-tailed test. And this is just a question of if a certain mean is different from another value. So in this example, we have there is no difference in this school's performance on the STAR test compared to the national average of 10, which is made up. Now the alternative would be there is a difference in this school's performance on the STAR test compared to the national average of 10. Now notice how we're not making an assertion if they're doing better or worse. We just think that they are different. So this is a two-tailed test. We have a tail here and a tail over here. And we are testing to see if our mu is going to be equal to 10 or not equal to 10. So two-tailed tests are just testing for a difference. We are not making any assertion of direction, whether it's going to be more or less than. But in one-tailed tests, we are. So let's first look at the one-tailed left test, where we are checking to see if something is less than a particular value. So let's start with the alternative, because that makes a little bit more sense. The school's performance on the STAR test is less than the national average of 10. We are checking or testing to see if this school is doing worse than the national average. This is what we think as the researcher, and we need to test it. So our alternative is mu is less than 10, that national average. The null hypothesis then would be that this school's performance on the STAR test is greater than or equal to the national average, and there's nothing going on. And here is that notation where mu is greater than or equal to 10. Now if we want to test the other direction to see if something is greater than, we can use a one-tailed right test. Let's again start with the alternative. We're saying this school's performance on the STAR test is greater than the national average. We think they're doing better. So we are going to write it out as mu is greater than 10, and the null would then be mu is less than or equal to 10. So when it comes to the one-tailed tests, one little way to maybe help you is to notice which way the gator is chomping. Remember that? It always wants to eat the bigger piece, that null, and it also kind of points in the direction of the alternative hypothesis. But probably the best thing to do is draw the picture. Drawing the picture is going to help you stay oriented, and it'll help you tie the realistic world to the statistical world. If I say that I think that this school is doing worse than the national average, do you think it would be on the left side or on the right side? It'd be on the left if you were to draw it, because down here we're going to have lower values and lower numbers. So draw the picture. That's the take-home message. Draw the picture, it'll help. So when you have to answer these questions, how do you know if it's a one-tailed or a two-tailed? You can ask yourself, is there any suggestion about how the two groups might differ? Is there a direction involved? So do you see words like more or less, or is it just suggesting a difference in general? So a two-tailed, which is non-directional, will usually say something like, do the groups differ? A one-tailed will say something like greater than, more than, less than, fewer than. It'll make some assertion of direction. And again, draw the picture. It'll help you, I promise. Here are some examples, and I really do want you to pause me for just a moment and try answering some of these. Test yourself. How'd you do? Let's go through each one at a time. An emergency room advertises a wait time of 10 minutes, but you believe that it's longer. It most certainly is. So I like to start with the alternative because usually that's kind of the thing that's explicitly stated. And once you know the alternative, then you can write the null just in reverse with the equality symbol. So here, we think that the wait time is longer than 10 minutes. Definitely. So our alternative is mu is greater than 10. Now that we have our alternative, you just mirror that, and our null then would be mu is less than or equal to 10. Now let's look at number 2. A psychologist believes that watching 9 or more hours of football a week reduces men's self-esteem. The average score for men is 40 points on a self-esteem questionnaire. So, there are two words here that are a little bit conflicting. We see the word 9 hours or more, or reduces men's self-esteem. Which one do we actually care about? Which is the value that we're testing? Is it something to do with 9 hours, or something to do with self-esteem? It's the self-esteem. This is a dependent variable that we care about. So we see the word reduces, so we know we are dealing with a left-sided one-tailed test. So I would write the alternative first, which would be mu is less than 40. The null then would be mu is greater than or equal to 40. And number 3, researchers report that infants can listen for an average of 8 seconds before becoming distracted, and most adults now. A psychologist believes that with training, infants can improve their attention span. Here is our key word here. Improve. So that means to go up. So our alternative would state that mu is greater than 8 minutes. And our null would be mu is less than or equal to 8. Here's another round of hypotheses to test yourself on. So pause me again and give it a go. How was it? Let's start with number 4. The average amount of lead in water is 2.8 parts per billion, but you think that one city's water levels may be higher than 2.8 parts per billion. So here is the important word, higher than. So our alternative is going to be the greater than symbol. Mu is greater than 2.8. Our null would be mu is equal to or less than 2.8. There is no lead in this water, it's fine. Number 5. It is suspected behavior modification will have an effect on the average number of sodas a person drinks in a week. This particular person drinks 8 sodas a week. So, is there any assertion of increase or decrease? No. In this case, we're just saying unaffect. It's going to be different after behavior modification. Maybe it'll go up, it won't. Or maybe it'll go down, hopefully it will. Do the behavior modification extra credit. So here we have mu is not equal to 8. We think that after a few weeks of behavior modification, it will be different from 8, but we're not saying whether it's going to be more or less. And our null is just that mu is equal to that 8, that it doesn't change. Number 6, you want to test whether a new smoking program actually reduces the average number of cigarettes smoked in a day, in this case 9. So we have a key word here, reduces, lowers. So we're dealing with a one-sided left tail. Our alternative hypothesis would be mu is less than 9. Now that we know the alternative, we just mirror it and put the equality, and we have mu is greater than or equal to 9 for our null hypothesis. Done it. We have gotten past the first step of hypothesis testing, stating the null and alternative, and now we know we always come from the assumption that the null is true. It's going to be very important. Keep that in mind. Next up, we're going to look at the level of significance. We're going to choose the appropriate statistical test, find our critical values, compute our test statistics, and formulate our decision whether we reject or fail to reject that null hypothesis. I will see you there.